Hello guys. Hello guys. Hello guys. Hello guys. Hello guys. Um, Late night. We are going to. Can you guess it or not? Can you guess it or not? What we are going to do? We want to read the paper I promised. Let's go over it. Recommender system. Last night we downloaded it, I guess, and it is the time to read it. We want to read a paper. We want to read the paper. What is the paper's name? Learning collaborative information filters. I think it is one of the basics of recommender system. And just waiting for us to read the fuck out of it. University of California, Irvine. Show us what you got. Are we recording? Yeah. Predicting items a user would like on a basis of, by the way, we just want to get an idea. We don't want to read it line by line, nor like deep into the formulas. So let's go fast. Predicting item. Can we finish it in an hour? Let's see if we can finish this paper in an hour. So it talked about collaborative filtering, and it seems that collaborative filtering and machine learning are not exactly the same, because predicting items a user would like on the basis of other users' rating for these items has become a well-established strategy adopted by many recommendation services on the internet. I guess Netflix was one of them. So it says collaborative filtering task that allows the application of virtually any machine learning algorithm. What is collaborative filtering? I don't know. We will figure it out. So current ones, 1998, has some shortcomings. Best performing algorithm is based on the singular value decomposition, SVD. Is it the same thing that we are learning in the SVM Andrew NG course? I'm not sure. Is it SVD or SVM? Of an initial, but SVD is like you decompose a matrix into like diagonal, which are sigmas, and then there is two, I guess, unitary matrix. Our best performing algorithm is based on the singular value decomposition of initial matrix of user ratings, exploiting latent structure that essentially eliminates the need for users to rate common items in order to become predictors for one another's preferences. I don't know. Large database of user rating for motion pictures and find that our approach significantly outperforms current collaborative filtering. Of course, your approach should outperform. When you're writing a paper, it should propose something novel that works better, at least in one area. Introduction: research on intelligent information agents in general and recommendation systems in particular has recently attracted much attention. My attention. The reasons for this are twofold. First, the amount of information available to individuals is growing steadily. Information overload has become popular. Wow, information overload. 1998 information overload they had. What do we have now with like reels and motivational content on Instagram? Has become a popular buzzword of our times, and people feel overwhelmed when navigating through today's information and media landscape. Well, maybe then they were watching news. This leads to a clear demand for automated methods, commonly referred to as intelligent information agents, that locate and retrieve information with respect to users' individual preferences. Second, the number of users accessing the internet is also growing. Like back in the day, it was back in the day. Okay, let's skip this shit. So, okay, I think that was common in recommender systems. The underlying techniques used in today's recommendation systems falls into two distinct categories. One, content-based. Like, what is content-based? Like, some movies are similar to each other. So you say, okay, this guy liked, tell me, Heat, he will like Casino. Maybe, I don't know. Collaborative method says these people like this movie, this guy had a similar taste to them on other movies, he might like this one as well. Content-based methods require textual description of the item to be recommended and draw on results from both information. Collaborative methods recommend items based on aggregated user ratings of those items. Web pages, news stories, movies, music videos, books, CDs, restaurants, and many more. Okay. Firefly, Wisewire. I don't know what they are. Recommendation, okay. Recommendation systems and advertisement. Like-minded users. Collaborative filtering can be seen as a classification task. The problem has not received much attention in the machine learning community. So we briefly present the central ideas of previously reported collaborative filtering algorithms. So we will have a recap, then they identify the main shortcomings of these approaches and motivate the need for techniques that do not suffer from these limitations. An artificial neural network is used to compute final recommendations. Section 2, collaborative filtering algorithms. Recommendation system Ringo. It was a music recommendation system. Intuition. Their algorithm was based on a simple intuition. Predictions for a user should be based on the similarity between the interest profile of that user and those of other users. It's kind of collaborative. They compute similarity between users, and whatever a new one likes, the other one gets. Okay, so they compute U and J, like it is now possible to define similarity measure between two user profiles, U and J. We have user U, we have user J, we have a similarity measure, Pearson correlation coefficient, RUJ. Let me highlight these parts because once we get back to them, I think it's a good basic read on recommenders system. So we have this metric. Once the similarity between profiles has been quantified, it can be used to compute personalized recommendations for users. Like all the users whose similarity is greater than the threshold, they are in a class or cluster. And if your threshold is too high, your clusters will be very small. UX is a rating to be predicted for user U. So UX for the on item X, right? How much user U, how much we predict user U likes item X. We have JX, J is the other user. So UX is U bar, what is U bar? Plus this ratio, JX minus J bar RUJ. I think U bar is the mean of U over X's, right? I guess, yeah. So JX says RUJ over sum of RUJ. It's kind of a mean. Okay, we have RUJ also. So U is a vector, U bar is a vector, right? Or no? So I had this in another video. That's very good. So we have the formula for RUJ. What is U bar, by the way? Is mean of U, for sure. So we have U for different X's, and if we take the average, it will be U bar, and UX will be, well, over J other users who rated X and their RUJ is greater than T, right? For all of those who rated X and their RUJ is greater than T, we can compute this. However, I don't know what is this RUJ definition. It has 3 sigmas. I don't know what they are about. So we have to make sure what those sigmas, what is the summand on sigmas. Okay, correlation based predictions were shown to perform well, but they suffer from several limitations. 3 specific problems. First, correlation between 2 user profiles can only be computed based on items that both users have rated. Right, makes sense. The summation and averages in the correlation formula are only computed over those items that both users have rated. So if the matrix is like kind of sparse, we have problems. And if there are thousands of items, the odds that they choose the same stuff is low. Like in Netflix, right? Second, the correlation approach induces a one global model of similarities between users. The correlation approach induces one global model of similarities between users. What is wrong with that? Rather than separate separate models for classes of ratings. What does that mean? Positive ratings versus negative ratings. I didn't get it, to be honest. The correlation approach induces one global model of similarity Okay, so it says the current approach measures whether two user profiles are positively correlated, not correlated at all, or negatively correlated. However, ratings given by one user can still be good predictors for ratings of another users, even if the two user profiles are not correlated. So two user profiles are not correlated. How that can be helpful? I don't get it. Consider the case where user A's positive ratings are a perfect predictor for a negative rate from user B. However, user A, like whatever user A likes, user B dislikes. However, user A's negative ratings do not imply a positive rating from user B. The correlation between the two profiles could be close to zero, thus potentially useful information is lost. I didn't get the second part. We can leave some question mark here. Let me know if you like to see the paper, but come on, dudes. I'm descriptive enough. However, user A's negative ratings do not imply a positive rating. Okay, it'll be third one. And maybe I didn't understand the second one. Most importantly, two users can only be similar if there is overlap among the rated items. If users did not rate any common items, that makes sense. They talked about it before. Did not rate any common items, their user profiles cannot be correlated due to the enormous number of items available. Dude, how much movies and shows Netflix produces? Like, I think we have one show for every person on planet. We don't have enough time to look at their teaser even. It's crazy. I want to know, in 1998, what was the platforms they were talking about? It was maybe the music. And it is crazy that there are some movies that everybody likes them. Even though everybody has thousands of choice, it shows that we have similar taste, but also the recommender system and these collaborative methods help some movies to be seen better. Actually, this is a very good idea. It is really close to what my thesis wants to study, because we want to study if something is being shown enough, other people it will get a kind of a, I don't know, what is it called? Everybody wants to see it. Like, if it is good enough, some people see it, they leave a good rating, then it is the job of recommender system. It will show it to other people, and people have similar taste, and they will see it, and they will like it, and its popularity or whatever popularity increases, and it goes viral, right? It's about going viral. Okay, now, due to the enormous number of items available to rate in many domains, this seems to be a serious stumbling block for many filtering services, especially during the startup phase. However, just knowing that users did not rate the same items does not necessarily mean that they are not like-minded. Consider the following. You just happen not to see. User A and B are highly correlated, as are users B and C. This relationship provides information about similarity between users A and C as well. However, in case user A and C did not rate like, so it's user A and B's ratings are similar because they had a common set. What if their common set is for mutually exclusive from B and C? B and C are similar, A and B are similar, but our system cannot find out that A and C are similar. It just says A and B and C. Ooh, it's been 26 minutes already, alright. Section 3, let's go. Collaborative filtering as a classification problem. Well, we want to classify users that are close to each other, right? Damn, I have to wash my hands. In this section, we present collaborative filtering in a machine. This section, we present collaborative filtering in a machine learning framework. That's good. I like to know machine learning frameworks. Well, we know some of them, right? We had the machine learning course up to section 6, so we know some shit. It's not as scary anymore. Yeah, give it to me. Machine learning. I will teach your machine like a bitch. Okay. Machine learning framework and suggests the use of an algorithm that specifically addresses the aforementioned limitation of correlation-based approaches. Collaborative filtering can be seen as a classification task based on a set of ratings from users for items. We are trying to induce a model for each user that allows us to classify unseen items into 2 or more classes. So based on what they like, we want to classify the items they haven't experienced into 2 or 3, like if they like it or if they don't like it, right? So initial data is a sparse matrix. Rows are users, columns are items, matrix entries are ratings. So this user watched this item, what is his rating? And if he didn't watch, what should we put? I don't know. Okay, sparse means that most elements of the matrix are empty, not 0, for example. We want to complete that matrix. It's called matrix completion, probably. So every user, they want to assign to them one regression model. So we have a table 1, which is a sparse matrix. And user 4 doesn't have a rating for item 5. but we have some other ratings from him. And then there is, for example, user 3 that also has rating on the same items. So one feature is missing. What are we going to put in that? Is it the average of the others? So okay. So based on the rating, they are simplifying the rating to discretizing it to like and dislike. Okay, I see. So you want like, you want dislike. And creates that exemplary feature vectors. After converting a dataset of user ratings, which was the first table, how did they convert it though? For items into this format, we can draw on the machine learning literature and apply virtually any supervised learning algorithm that through analysis of a label training sample, EJ and CJ can class and what is E? Class and E can induce a function f from E to C. Okay, I didn't read this part carefully. So we have a table of rating. Some elements are missing. Here they are transforming this table to another table of exemplary feature vectors that says either if a user likes something or not. Oh my god, I'm tired as fuck. Tired. Sorry for the emails, by the way. Let's not get distracted. This one. All right. Okay, we have table 1. Consider that we would like to predict user 4's rating for item 5. U for I5 is question. We can train a learning algorithm with the information that we have about user 4's previous rating, like item 1, item 2, item 3. In this example, user 4 has provided 3 ratings, leads to the 3, I1, I2, 3. These training examples can be directly represented as feature vectors. Okay, feature vectors. That is some machine learning shit they dropped there. Where users correspond to features U1, U2, U3. Users correspond to U1, U2, U3. So we separated user 4, which its rating is under question. The 3 remaining users, we are making a table out of them. I will make a table out of you, motherfucker. And the matrix entries correspond to feature values. Okay, feature value. It's a conversion of table to another table. User 4's rating for I1, I2, I3 are the class label of the training example. Because we have user 4 doesn't have a rating for item 4, he has rating for item 1, 2, 3. We want to know his rating for item 5. So we don't give a fuck about item 4. It seems that's like that. And we keep the 3 remaining users with their ratings about item 1, 2, 3. Because we don't know their rating about item 4. Also, we don't know their, like, user 1 and user 2, we don't know their rating about item 5. So let's see what's up. Okay. Shares values. If the learning algorithm to be used cannot handle missing feature values, we can apply a simple transformation. Transformation is also a word, guys. I know they use it in machine learning. Amin is a great transformation guy. Note that we cannot introduce an additional numeric value that indicates a missing feature. Because this would conflate the new value and the observed ratings. However, every user can be represented up to n Boolean features. Okay, this part. Every user can be represented by up to n Boolean features. What is n? Where n is the number of points on the scale that is used for rating. N is the number of points on the scale. What is points on the scale? I don't get this. Let's highlight this with yellow maybe. This sounds a bit, yeah, we can go back to it later. Yellow is an alarming color. Every user, so they want to represent users by n Boolean features. Number of points. We are going out of charge, by the way. I hope you have like 15 minutes. That is used for ratings. if the full endpoint scale of ratings is used to represent ratings from end users. Full endpoint scale of rating is used. I'll leave a question mark here too. The resulting Boolean features are of the form user M's rating was I, where I is between 0 and N included. 0 excluded on it. So 1 to N. We have N features 1 to N. Boolean features are of the form user M's rating was I. What does it mean? Was I? For I. We can now assign Boolean feature values. I have to bring Dr. Mesh for reading these fucking papers. Actually, I texted him. He said, he'll let me know, but I won't wait, so I will say let's do tomorrow. Alright, we can now assign Boolean features value to all of these new features if this representation leads to an excessive number of features that only appear rarely. Dude, motherfucker, write these sentences in a way that a human being can understand it. What the fuck? We can now assign Boolean features values. I didn't understand what was the Boolean feature. Now they have values. Well, it is 0 or 1. Okay, let's be honest. To all of these new features. What are the new features? I don't know them. Dude, let's go fast. I don't think there's any value in spending too much time on reading papers. We just want to get to know the space. If there is a good paper we are interested in, we can mark it and go into the details faster. First step in every paper is that we are going fast. Alright, let's go fast. Let's go the fuck fast. Okay, I went very fast and it was nothing. It is easy paper, but it's fundamental. So they make another table. We have a first table. Sorry, let's not get into the details. They have one table which is missing some elements. They make another table to do machine learning. I didn't get this part to be honest. If this representation leads to an excessive number of features that only appear rarely throughout the data, the rating scale can be further discretized into the two classes like and dislike. The resulting representation is simple and intuitive. Training example E corresponds to an item. The columns of the new table are E corresponds to an item that the user has rated. So it is I1, I2, 3. Or it is different. The class label C is the user's discretized rating for that item. Is it like or dislike? Okay, I think it is like. For user 4, we had 1, 2, 3 as items he rated. And his rating for item 1 was 4, for item 2 and 3 was 2 and 1. I think, okay, yes, and the class is, he liked first one, because the first one was above average, and he disliked second and third one because they were below average, so makes sense now. And now we are FI. What is FI? Is the user described as an item, and items are represented as vectors of Boolean features Fi. Alright. U1 likes, okay. And now for the remaining users, it is creating two rows of the things he likes and the things he doesn't like, which I1 and I3, item 1 and item 3 he likes. There is nothing that he doesn't like. Makes sense. I think I got the how it transforms to tables. For user 2, he doesn't like item 2, item 4 we don't care. Yep. Item 3, user 3, he likes item 1, item 4, item 2, he doesn't like item 3. Alright, all good. But we could, I don't know why we have two rows. Like one row could be like, and 1 stands for like, 0 stands for dislike. Oh, maybe, okay, now, okay. We have two rows because, for example, user 1 has no rating for item 2, therefore, E2 in both rows is 0. So, alright, I think I get it, how he makes it. I need some water. For user 4, where rating of either 1 or 2 corresponding. Now that we have this new table, we can draw a machine learning literature and draw on the machine learning. Any supervised learning algorithm that through analysis of a label training example T, EJ, CJ. What was C? C was the column, the class. Alright. E, the class label C. Okay. C was for the user himself, what he rated. So we have EJ and CJ. What is J? Is the other users can induce a function E from. Let's go. I think there is this function. Okay, we can make a function from these pairs of EJ, CJ. Alright, that's not very difficult. So we have this EJ, CJ pairs that we made in the new table. We can come up with machine learning. We can come up with a regression function or classifier function that says what is the function that maps E to C, and now we can use it now that we have the features for other users on the item 5. We can use them to the same function to find if user 4 likes or dislikes. However, if we look back at the correlation-based approach described earlier and express them in our learning framework, we notice that these algorithms solve the classification in somewhat unconventional ways. So that was more of a rating estimation, I guess. This is unconventional. All right. Prediction for unseen examples are then computed as a weighted average of feature value. While this approach seems to work reasonably well for the domain at hand, it is not supported by a sound theory that we could use to motivate the algorithms used for either regression test. It comes as no surprise that researchers in machine learning have thus far not attempted to solve any task with this algorithm, the rating one. It seems likely that theoretically well-founded algorithms that have the discrimination between classes as their specific goal cannot perform correlation-based. Okay. So we can outperform correlation-based approaches. By the way, we talk a lot about mental masturbation, but there are uses of abstraction that helps us find better algorithms. Like here, so it is good as long as we keep in mind that these solutions we make need to be useful in practice, and if some of them are, it's very good. Reducing dimensionality. Am I tired? Are you tired? It has been 52 minutes and really I am tired. Okay, I don't want to go to section 3.1. Let's stop here. Thanks for watching.